Hello everyone. This is the last video in a series of amazing rotational videos that have gotten you through this topic with supplemental education. I don't know what I'm talking about. I just tried to use some big words. What do you think? Anyway, this video is to help you with rotational momentum or angular momentum. And it's pretty straightforward. In the past, as you can see here, we've done translational momentum, where it's just the sum of momentums in the beginning equals the sum of the momentums in the end. If the masses are stuck together, we add their masses together. If they start together, we add their masses together at the beginning, whatever. But the angular or rotational version of momentum, hello, that's new. Okay, let's try that again. I'm going to keep that in there. We ain't editing nothing. You see the real deal behind the scenes. Anyway, it's L equals I omega. Now, we've probably already discussed this in class, but hopefully this isn't a surprise. I mean, mass is like, moment of inertia, and translational velocity is like rotational velocity. So instead, now, you just replace it with angular stuff like I, A, omega, A initial, plus I, B, omega, B initial. Afterwards, let's add their final momentums. And by momentum, I mean angular. Oops. See, I'm talking and I'm screwing up. That shouldn't be a B. That should be an A. Omega A final. Omega B final. And if they're stuck together, guess what you're doing with their moments of inertia? You're adding them together. Craziness. All right, this is a very typical example. There's numbers to it. It'd be much easier if it was algebraic, but I've also seen this as a very simple multiple choice question. So you're supposed to be able to do this rather quickly in terms of algebraic, but here we go. So we've got a disk that is spinning and a disk that is not spinning. And we just add their initial angular momentums and their final angular momentum, and that's it. So you have, this is a disk, so it's 1/2 mr squared. You have a disk that's rotating, the larger one, so it's 1/2 3 kilograms times radius squared. That's your moment of inertia, 1/2 mr squared. And it's rotating initially at 8 radians per second. Can you tell I have not had coffee in a while? The other one's at rest in terms of rotation, so you don't have to worry about it right now. Afterward, they are stuck together, so I'm going to add their moments of inertia together. So that's 1/2 3 kilograms. Sorry if you heard that in the background. I have a cat that's going insane. Plus, does that say 1/3? Wow, this is a video of a lot of mistakes. 1/2, and then the other mass is 1 kilogram with a radius of 0.15. Picture not drawn to scale. Final angular momentum. Doing a little mathy math, we would get that, oh boy, that's just crazy units here. We would get 0.48 kilogram meters squared per second, wow, equals 0.07125 kilogram meters squared omega final, and omega final is 6.74 radians per second. That's it. I mean, seriously, it's just conservation of angular momentum. So instead of them moving in a straight line in one dimension, this is just adding their spinning momentums. No big deal. Let's do another example, because one is just not enough. Scrolling down, scrolling down, scrolling down. Now this picture was not drawn by me. This picture was taken directly from AP, because I don't understand it. AP, for whatever reason, seems to like this lump of clay hitting a rod and then they spin or something like that. They also ask questions in terms of systems, which we will get to at a later time. But it's the same idea. We have the I for the clay and its initial angular momentum plus the I for the rod and the final angular momentum for the rod. Afterwards, they are stuck together. Does it say they stick together? completely inelastic. Same thing as perfectly inelastic. So we have I clay plus I rod and omega final. I see it. Why did I write final there? What's wrong with me? All right, let's sub in some stuff here. We have I for a single mass moving. Now, this one you should really just know for your AP exam. It's just mr squared. Okay, so, but what is r? At the point of impact, which is right here when we're talking about the collision, the r is the same thing as the length of the rod. That is the distance from the mass to the point of rotation. So we have mr squared, so that's 0.5. Actually, slow down. What I want to show you is this. It's mr squared. That's the moment of inertia. And we are asked for the angular velocity afterwards. Okay, here's a problem. Well, it's omega, but I think they give us a speed in terms of meters per second. Interesting. How are we going to deal with that? There's a couple options. Well, omega is v over r, which I'm actually going to sub in here, and then I get mr squared v over r, which equals mrv. Now I'm going to address this again in the recap of this amazing video, but that seems to come up a whole bunch. AP seems to like a single mass moving, and its angular momentum is mvr or mrv, however you want to say it. But here we go. Subbing in some numbers. We've got 0.5 kilograms. When it collides, it's at a distance of 0.3 meters, and its velocity is 10 meters per second. Afterwards, they are stuck together, so we add their moments of inertia, which is 0.5 kilograms times L squared, which is 0.3 meters. And the moment of inertia for a rod rotating about its point is 1/3 ml squared. And that's going to be 1/3 2 kilograms, length squared, and then final angular velocity. Now, if you notice here, this is not algebraic, and if it was, it would be a little bit easier. But there is an r in every term. So that might help you in terms of solving this algebraically. One of the r's will divide out. And then we get omega final is simply 14.3 radians per second. You don't need to see me do all the math. You can just trust that I'm a genius and I got it right. I hope I got it right. If I made a mistake, let me know. All right. I mean, that's basically it for angular momentum. It's the same thing as translational momentum, but we do I omega instead of mv. Let's summarize this puppy. How about it? As we scroll down, we see that instead of using what we used to do for translational momentum, which was, MAVA initial plus MVVB initial, so on, we use I omega, which hopefully makes sense. The whole rotation topic, instead of mass, we use moment of inertia. Instead of velocity, the angular velocity would be omega. Same thing. So it's the same conservation of momentum expression, but with different variables. And if they're stuck together, instead of adding masses, you add moments of inertia. Simple as that. And for whatever reason, AP seems to love a single mass moving. I don't know why, but it comes up in a lot of multiple choice. It has been on an FRQ in the past, so I don't know if they would do it again. But the angular momentum is just I omega. I for a single mass moving is mr squared, and omega is omega, but we replace omega with v over r, and the one of the r's divides out, and you're left with mrv or mvr. Now, the r is the distance from the moving mass to the point of rotation. If it collides with a rod near its end, then the distance from that location to the point of rotation is the length of the rod, and that seems to happen often with these questions. And then finally, something that was not addressed in this video and usually shows up as a multiple choice. If it's simply a single object rotating, momentum is still conserved. You have the initial moment of inertia times the initial angular velocity has to equal the final moment of inertia times the final angular velocity. Now, these things can change. I'm sure we're going to be doing an example in class, but the easy example is like an ice skater or a diver or a gymnast, anybody who changes the way the mass is distributed along their body. Initially, a ice skater, for example, may go into the jump with their arms out and they leap up into the air. And then they pull their arms and legs in, decreasing their moment of inertia. So the final moment of inertia for them spinning is less than what they started with. Therefore, the angular velocity must increase, and that's why they spin faster. Then they land, they open their arms, extend a leg. You have more mass located farther from the center of rotation, so their moment of inertia goes up and their angular velocity goes down. And one last thing, they often connect questions like this to rotational kinetic energy. So just be aware of that. I'm sure we'll cover it. But other than that, I've bored you enough, or have I enthralled you enough? I'm not sure. Because of that, I can only give this a rating of 3 out of 5 stars, but I wouldn't change a thing.